Section 5.7. Classify the zeros of a polynomial function. We're going to start off with the fundamental theorem of algebra. And the fundamental theorem of algebra states that if you have some polynomial with a degree of n, where n is greater than 0, you can have a degree of 0, or it would just be a constant, then if you set that equation equal to 0, that polynomial has n roots, or n solutions. So if you have some polynomial with degree 3, that means that that polynomial has 3 roots, or solutions. If you have a polynomial with degree 287, that means that there are 287 roots or solutions to that polynomial. So let's look at this example I have down here. The directions ask us to find all the zeros of the function. Now we have a lot going on here because we have a polynomial starting with x to the 5th. I have the graph right below here to help us out. We can tell that it's an odd function, so our graph is good, and it's in opposite directions. The first thing we're going to do is list the possible zeros. That's going to help us out here. Remember, the possible zeros are the p over q, which is all the factors of our constant term over our leading coefficient. So our possible roots, or our possible zeros or solutions, are all the factors of 14 over 1. So our possible solutions are plus or minus 1, plus or minus 2, plus or minus 7, and plus or minus 14. Now, just like in the last section, we're going to use the graph to try and help us figure out what we should start dividing by. By looking at this graph, we can see that we probably have a 0 at -1 and 2, so we can start there and start dividing by those numbers. I'm just going to start off dividing by 2. So we'll use synthetic division, and we'll start by dividing by 2. Write down all the coefficients of our polynomial. So we have 1, -4, 4, 10, -13, and -14. And then divide. So bring down the 1. 1 times 2 is 2. -4 plus 2 gives us -2. Then we have -4. Add those together, we get 0. Multiply, get 0. Add 10 plus 0, we get 10. Multiply 10 times 2, we get 20. Add -13 and 20, we get 7. 7 times 2, 14. So we get a remainder of 0, which is perfect, exactly what we wanted. So we know that 2 is a 0, or a root, or a solution, all the same thing, of this polynomial. So we have 1 down and 4 to go, because we have degree 5 here, and the fundamental theorem of algebra tells us that we have 5 solutions of this baby. So next step is we're going to divide by another possible root, and by looking at our graph, we're going to say it's -1. And when our graph approaches the x-axis and just touches it and comes back down but never really crosses it like it did over here on the 2, that means that there's a double root there, and there are actually 2 zeros that are -1. So we're going to divide by -1 twice. And I'm just going to actually leave these coefficients like this and divide again, so I don't have to keep rewriting those coefficients over and over again. So next I'm going to divide by -1. So same steps. Bring down my 1, multiply the 1 times -1, get -1. Add those 2 lines. Remember, synthetic division, you're always adding these 2 lines. So -2 plus -1, -3, multiply. We have a positive 3. Add together, we got 3, multiply, 3 times -1, -3, subtract. We have 7, multiply. We have -7, add those 2, we get a remainder of 0, which is perfect again. That means -1 is also a 0, or root, or solution of this polynomial. So I said that -1 was a double root, so I'm going to divide by -1 again, and it should be that I get remainder 0 one more time. So I bring down my 1, multiply -1 times 1, -1, add these 2 lines. -3 plus -1 gives -4. Multiply those, get +4. Add, get 7. Multiply -7. And look at that, we get a remainder of 0 again. So we have found 3 solutions or roots of this graph so far. But now we're kind of running into a problem, because looking at our graph, I don't see any more possible zeros. I don't know about you. So what that means is that there are 2 imaginary zeros that we can't see. So to find those, we have to move away from the graph now. We know we have 3 zeros right here. And now we're going to look for our imaginary zeros. So to do that, we're going to take the factor that we have left over. So we're going to use these coefficients right here to write our factor that we have left over. And we divided 1, 2, 3 times. So that means we go down 3 degrees. So when we write our factor left over, it should be x squared minus 4x plus 7. So right now we're looking at, we know we have factors of x minus 2, x plus 1, x plus 1 times x squared minus 4x plus 7. So now what we have left is to factor this, but if you looked at it, you can't really factor it. There's not 2 factors of 7 that add to give you 4. It doesn't work out. So we're going to pull in our bag of tricks, dig back deep, and you're going to pull out the quadratic formula. Yes, the quadratic formula. I said it. Now you're probably saying, oh, I know that right off the top of my head. It is negative b plus or minus the square root of b squared minus 4ac over 2a. And I'm going to say fantastic. I can't believe you still have that memorized. It must be the fantastic song that your teacher taught you. How awesome is that? So our last step is to use this quadratic formula. Remember that this is a, b, and c. The coefficients in front of our variables don't include the variables. So if we fill in this formula to factor, we're going to have negative times negative 4, which is going to turn it positive, plus or minus the square root of negative 4 squared minus 4 times a, which is 1, times c, which is 7, all over 2a. Now we compute what's under the square root, and here the negative 4 squared is going to be 16 minus 28. I'm just writing above here what this equals. So our next line, I'm going to move down here. I'm going to have positive 4 because that negative times a negative, plus or minus the square root of 16 minus 28 gives us a negative 12 all over 2. Now remember, when you have a negative under a square root, you need to pull that out. Have that be an I. And you can simplify the square root of 12. You can rewrite the square root of 12. I'm going to write this out step by step here. As the square root of 4 times the square root of 3. And the square root of 4 you know to be 2. So your next line would be 4 plus or minus 2i square root of 3 all over 2. And you can simplify that 4, 2, and the 2. If you divide by that 2, you are left with 2 plus or minus I square root of 3. So your 2 complex solutions are 2 plus I square root of 3 and 2 minus I square root of 3. Now that we have found all 5 zeros of this polynomial, you now know all the factors of this polynomial. From above, we divided this polynomial by 2. So we know that one of the factors is x minus 2. We also divided by negative 1 twice. So we know we have factors of x plus 1 and x plus 1 again. I'm just going to write x plus 1 squared because that is the same thing. And we just found our 2 complex zeros. So our other factors are x minus 2 plus I square root of 3 and x minus 2 minus I square root of 3. I know it looks funny, because they're complex numbers, but this is your polynomial completely factored. And we know from this that our zeros are 2, -1, -1 again, 2 plus I square root of 3, and 2 minus I square root of 3. You have just found all the zeros of this polynomial. Congratulations!